Our project is called DACARA, and it's the rural cold chain solution. More than 3 million people die per year from diseases preventable through vaccines. 1.5 million are children less than 5 years old. An estimated 19.4 million children under the age of 1 do not receive the basic vaccinations and are not protected against these preventable diseases. 60% of these children come from the same 10 countries. The Global Vaccine Action Plan is trying to reach out to these children to provide better access to vaccines by 2020. To ensure this happens, vaccines are being shipped to places following the constraints of the cold chain. The cold chain is a series of temperature-controlled environments through which vaccines and medications are shipped. Theoretically, these vaccines are kept within a range of 2 to 8 degrees Celsius. However, this process is not entirely effective. Across the entire vaccine cold chain, instability of temperature occurs at least once in 75 to 100% of shipments.
Most of this instability occurs during the end of the cold chain, especially in rural areas where products are transferred with only ice and a styrofoam cooler or a lunchbox for up to a few days. When the vaccine temperature is out of range, the vaccine loses its efficacy. Our goal is to create a product that can better control the temperature of vaccines in order to provide vaccines to as many people as possible, no matter how rural the area. In rural areas, transport is usually done by car, bike, animal, or potentially drone. Therefore, we decided that it must be a small and lightweight container.
This is the current setup being used. It follows the necessary requirements to fulfill the 3 layers needed to ship vaccine vials. The innermost layers are the vaccine vials, then the middle layer is a plastic bag surrounded by the cooling and insulation materials. These layers must be watertight. The outer layer must be rigid and is often the styrofoam cooler. We used a list of constraints, which are needs that had to be met by our design, and a list of objectives, which would ideally be met by our design. The device has to meet shipping standards by being at least 4 inches by 4 inches and less than 750 feet cubed, weighing less than 5,000 pounds, but it also has to be small enough to be carried by one person or animal for long periods of time. Based on OSHA standards, our product should be less than 15 pounds. The final product needs to have at least 3 layers, 2 of which are watertight, and be able to keep the temperature of the innermost layer between 2 and 8 degrees Celsius for at least 24 hours in extreme conditions, which we defined as -20 degrees Fahrenheit to 120 degrees Fahrenheit. Ideally, this product would be weather resistant, able to hold the temperature for a week, and reusable, biodegradable, or recyclable. We decided to change the design of the 2 innermost layers by making silicone molds to hold the vials in place during transit. The number of vials that can be placed in the container at once can be manipulated depending on how many vials are needed. We changed the cooling method to picrete, which is a frozen mixture of sawdust and water, because of its great thermal and mechanical properties. The picrete will be in the base of the mold, while the vials will be securely placed in a mold that is suspended into the picrete. A lid will then be placed on top to secure the vials in place. Insulation materials will be a combination of styrofoam and another material. Then the material for the outermost layer will be tested to determine the best for this application.
Since the mechanical testing wasn't completed at school with the styrofoam insulation and outer materials, a sample test was done using a Playmate igloo cooler with picrete and 4 vials. They were dropped from 6 feet high, which is more than the required minimum and approximately the height of a camel. All 15 trials passed, and none of the vials broke during testing. Some temperature tests were also conducted to determine which insulating material was the best. Overall, the Bazotect, or Magic Eraser, performed better than the aerogel in the oven testing, but the aerogel performed better in the cold testing. While we couldn't finish the temperature tests, we decided to determine the theoretical heat transfer of the outer layer, using picrete as the cooling layer at the maximum weight based on OSHA standards. By finding the specific heat of picrete, we could determine the heat loss over a period of 24 hours given an external temperature of 50 degrees Celsius or 122 degrees Fahrenheit. The heat loss allows us to simulate how insulation types may perform. Of the insulation we intended to test, the aerogel would theoretically be the most successful with the least amount of material. Further testing is still needed to determine which insulation types may work well in practice.
And finally, we created a simulation to model the changes in temperature that a container might experience while delivering the vaccines to more rural areas in the United States. In this example, it represents a vaccine being delivered from Detroit Metro Airport to Emmett County, Michigan. The vaccine will travel north along I-75 through 13 Michigan counties. Knowing the average temperatures along the route of delivery is crucial in determining the heat loss of the device over the course of the transport. If the vaccine is transported in the month of May, the average temperatures that the transport will experience is in the range of 51 to 60 degrees Fahrenheit. understanding how much heat loss can prevent the vaccines from going out of the 2 to 8 degrees Celsius temperature range. By making the vaccine stay within the 2 to 8 degrees Celsius range, we aim to help more people. From all the members at DACARA, we'd like to thank you for watching and taking the time to listen to our presentation.